Hi ladies, today we are going to be extending our idea of how light is equal to the wavelength times the frequency. So what ended up happening was Einstein used Planck's quantum theory to explain something called the photoelectric effect. And we'll get into Planck in just a second, but the photoelectric effect states that whenever you start to shine light rays onto some type of metal, they're going to excite them to a point that they're going to start shooting off electrons. And this idea here is the same as whenever I lit something on fire. I lit on fire different elements and they showed different colors of light. Some were green, some were red, and those were the electrons being shot out of those different metals that I was using. These lights are going to be called photons. That's the stuff that is being ejected out of the metal. So again, we have a metal here. It's being shot with different light rays or different types of energy, and it's going to excite our electrons in the metal to a point where they start to be ejected or emitted from that metal in different forms of light or even like different rays from our electromagnetic radiation. And all of those things are going to be emitted as photons. Now, Einstein said that light behaves as something slightly different than what we've thought about before. He said that they were in the form of particles. Just like how your pen and paper is made of particles, Einstein said that it's going to follow the same type of rules that a thrown pencil would. Whereas in other situations, we've already learned how light is going to be like a wave. And that's where we use this equation, where it has such a large wavelength and it occurs so often, or the frequency, that we can calculate the speed of light. So you have to consider that both light can contain both the idea of a particle as well as that of a wave. Now, here's an example here where you have to have a specific amount of energy to release that electron or that photon from the metal. So think about the metals before I lit them on fire back in lab. Whenever we were just looking at them, they looked just like ordinary things. Like I had salt, and that wasn't really that exciting. It was being hit with light rays because we had the lights on in the classroom, but it was below the threshold frequency to cause any electrons to be emitted. Once I started to light them on fire, they became so excited that electrons were emitted. And those electrons were emitted in different colors of our visible light spectrum. Now, if I were to be able to actually increase the frequency with which I hit that metal inside of the container, it would actually shine even a different color depending on how much energy I can put in there. So whenever we're looking to figure out how much energy a single quantum is absorbed or emitted, it's going to be using this equation right here. And this equation is called, is using Planck's constant, and it says that the energy is equal to Planck's constant, which I will show you in a second, times the frequency. And we've done this one before. We know that the frequency is this funky letter nu. Now, H is a different one. H is called Planck's constant, and we're going to say it is 6.6 times 10 to the negative 34th joules times seconds. Now, it's not the prettiest unit you've ever seen, and I agree. However, it is what it is. So here is Planck's constant. And I'm going to give that to you on any tests or quizzes, so you don't have to memorize it, but you do have to know that H is always going to be given to you. So as long as you know H and one of our other variables, you could solve for X just like you have in the past. Another way that you can write this equation is very similar. However, I know that we can write our frequency a little bit differently. Let's think back to our equation of the speed of light is equal to lambda times nu. Now, if we were to solve this equation using algebra for our nu, you would divide by lambda on both sides. Those would cancel, and we would get nu equals the speed of light, which we already know is 3.0 times 10 to the 8th meters per second. And that one will never change. It's always the same. And it would be divided by our lambda. So we can actually substitute that equation in for our v in this new equation that we have. So we could also use this equation as stated as energy is equal to h, because h is always the same. And then instead of writing v like we do over here, we're going to substitute what we know v is equal to, which is the speed of light over lambda. Now, the way that you know which one to use is it depends on what is given to you in an equation. So let's try one over here. So this question is asking what is the energy of a photon. So we should already know, that we are doing something with either E equals h times nu, or E equals h times c over lambda. And it says, what is the energy of a photon of microwave radiation with a frequency of this big number? So which equation uses frequency? Is it number 1 or number 2? Hopefully you picked number 1. So let's go ahead and write down what we know. We know that h is equal to 6.6 times 10 to the negative 34th joules times seconds. And we know that our frequency equals 3.20 times 10 to the 11th per second. All right, let's go ahead and plug in our equations, or our values into the equation. E equals 6.6 times 10 to the negative 34th joules times seconds, multiplied by 3.20 times 10 to the 11th over seconds. Since seconds is on the bottom and seconds is on the top of our fractions here, we know that they are going to cancel out, and we're going to be left with joules. And that's a really good thing to know, that energy is always in something called joules. So energy is going to equal 2.1 times 10 to the negative 22nd joules. And if you need that written out a little more pretty, you can use it here. Again, in our PowerPoint, we have a little bit bigger number for our h. It's the same thing. We're just going to use a slightly shorter version. And it goes through in nice detail all of those steps and gets the same answer. So let's try one more. It says, what is the frequency for a photon whose energy is this? All right, so we're looking for frequency, but we have two equations for energy. One is E equals h times nu, and the other one is E equals h times the speed of light over lambda. Okay, so if we are looking for frequency, we could use either the first equation or the second equation, but the second equation does not have the frequency in it. So let's use number 1. This is the one we want. So if we were to write down the information that we know, we have E is equal to 1.166 times 10 to the negative 17th joules. We have H, which is equal to 6.6 times 10 to the negative 34th joules times seconds. And we don't know our frequency. So let's go ahead and plug it into our equation of E equals H times V. And our E is going to be 1.166 times 10 to the negative 17th. And that's going to equal our Planck's constant. And times our unknown. So if we were to solve for x over here, we're going to divide each side by 6.6 times 10 to the negative 34th joules times seconds on both sides. Whoops, got ahead of myself. 6.6 times 10 to the negative 34th on both sides. Since joules is on top and joules is on the bottom, we're going to cancel those out, and we're left with per second. That is exactly what we need for frequency, since that is what frequency units are. It's either hertz or our number over seconds, and that's exactly what we've got. So once you put it into the calculator, our frequency equals 760 times 10 to the 16th hertz. Or if you wanted to write it in the way with seconds, you would take away hertz and put it over seconds, just like that. And you're all set. If you need a little bit cleaner version, there you go. Go ahead and pause it here if you need to. Okay, now that we have how much energy is in each wave, we can see what happens to those electrons as it is struck with each wave. So, when an electron is at its lowest possible state, when it is most comfortable, it's called its ground state. And a ground state for you would be probably lying in bed all snugly on a Saturday morning. However, whenever your mom and dad come in and tell you to wake up, they're going to excite you and make you move around. The same happens with electrons. So, whenever an electron is in its ground state, its principal quantum number is going to be the number 1. However, the more excited it gets, its principal quantum number is going to increase to larger and larger numbers, telling it's more and more excited. And the quantum of energy is usually going to be in the form of light, is emitted whenever that electron drops back down to a lower energy level. So once you have gotten all your chores done, you've gone to school, you've done all your work, you can go back to where you're most comfortable, back in bed, which is your ground state. Electrons are the same way. And so they have to show how much work they've done, so they emit light. So here is our example of hydrogen. Hydrogen can go to a couple of different states whenever it gets excited. Anytime that something goes to a higher level and then drops back down, it's going to emit some type of light. Now for hydrogen, remember we have specific emissions for each element, and this one is our hydrogen. Now when hydrogen goes from any excited state back down to the first ground state here, we would have something in the ultraviolet range going to be emitted. Now, I'm not worried about you knowing where these things are. Just understand that based on how far something travels and where it falls back down to, you're going to get different lights. So, for example, if you had something over in this range and it fell back down to our principal quantum level of 2, this is going to give you something in the visible range, such as something that's purple or blue or even red. You can even get other stuff that we don't see outside of our visible light spectrum, and that's whenever it is going to fall to a much higher energy level than that of the principal quantum number of 2. But again, we can't see it, so I usually can't use it as an example in lab. The best example is whenever you see a neon sign. You have to have lots of different elements in a neon sign, even though we only say that it contains one type of element. Now, it's really important that we have all these different colors because each different gas is going to have its own characteristic. And we saw this as a great example in lab. Of course, I love to set things on fire, so whenever I set stuff on fire, it was going to be different colors. Like you had the green one that you thought was from Harry Potter, and that was all based on how much was emitted when our electrons are excited and then falling back down to their ground state. Stuff that is pretty interesting to figure out what uses the greatest energy. Now we can say that we have different transitions from a excited state of n equals 2 dropping down to n equals 1, an excited state of n equals 3 dropping down to n equals 2, or that of 4 down to 3. Now you would think, oh, these all sound like they're exactly the same. However, let's take a look at A here. So if we were to go back up to our spectral lines, let's get that cleaner. Look at how close it is to our nucleus, which is in the center. That would be a lot of energy to have to overcome. So anytime you're getting closer and closer to that nucleus or our ground state, that is going to use the greatest energy and release the greatest energy. Now, remember, our light behaves like a wave as well as a particle. Matter is the exact same thing. It's pretty nifty, and we can use very similar equations. That's enough for tonight. I will see you guys tomorrow. Make sure you have some great notes.